some students, important question about substitution. Yeah. So here, the question, why we do the substitution, I need to explain a little bit. Yeah, this substitution. Okay. Yeah. All right. All right. Before I answer this question, Lucas, can you repeat your question? Yeah.
So, if we're able to manipulate the start point,
Yeah.
why do we use why do we change variable instead of just setting n equal to 0 with the idea that the summation has to equal the same value? So we just say n plus 2 and n plus 1, 8 n plus 2. You know what I'm saying? Is it important that we do the S substitution?
Yeah, it's important. All right. Yeah. All right. Okay. Yeah. So let me answer question in this way. Let me answer question from the root. From the root, you know, the fundamental. Yeah. All right. Yeah. Let me get my stick to but for the Zoom students. Yeah. Yeah. All right. So here. Yeah. Zoom student. All right. Yeah. Because Zoom students, they cannot see me, you know, doing things. Yeah. To make them see. All right. I still need to use my pen. All right.
Are you saying all of them is n minus 1 for the exponent?
No, I'm saying instead of just introducing S, because, well, I mean, I think it's just confusing us because we say with S equals n minus 2, it doesn't apply to the last 3 terms.
Right. That's right.
So I'm saying if we just kept it all as m and then just set n equal to 0, the summation, it would be wrong if we left it. So we'd say m, like the parentheses, m plus 2, instead of just using s. I just don't think I understand.
You can go straight into the m is equal to s plus 2.
What?
You can go straight to m is equal to s plus 2. Because we're just changing that exponent.
Yeah, but it's pretty much the same thing, I think.
Yeah. All right. Let me answer this way. All right. Yeah. Because if you do not go to the very beginning, the root, the fundamental thing, it's hard to understand. But here, let me point out the root part. So what's that? All right. So now, yeah, let me erase. Yeah, because a lot of things we do not need. We do not need to keep. Yeah. All right. Yeah. Some, very clean. Yeah, here. All right. First, I'd like you to focus on this equation. Yeah. We work on this equation. Now, make your observation on these terms. The general term. Okay. First summation, the general term, right? Second summation, the general term. Third summation, the general term. The general term. All right? Then, can you see something special? You compare these 4 general terms. Anything, you see something different? Right?
They're all equal except for 1.
Yes. All right. So for these 3 summations, we do not need to change anything, right? Yeah? Because they are fine. Okay? You can keep them. But the first one, the general term form is different from the remaining 3. Do we want to align it the same as the remaining 3? Make alignment, right? But that alignment is achieved by the special substitution. How about that? That's clear, right? So from the root understanding, because the remaining just algebraic manipulation, right? Yeah, substitution, you do carefully. Yeah. But from the root is, if you do not do this substitution, then it's hard to add the corresponding terms. How do you add the corresponding terms? Because our goal, we want to add corresponding terms. But this other one, make it harder to add the corresponding terms. But if we align with the same, because after substitution, can you see they have the same form general terms? because we only look at the x part. Coefficient part, we don't worry. Okay? Coefficient part, we don't worry. We look at the, x part. Same, function, yeah. Base function part, yeah. So, yeah. For the general term. So you can, yeah, straightforward. Yeah. So that's make it very clear. Yeah. But when you determine which summation you want to do substitution, which one you do, yeah. So you compare the difference. Okay. Yeah. Some summations you do not need to do any substitution. But some, the other one, yeah, you need to do some substitution. Yeah. All right. Good. Okay.
Factoring out the x to the basically, right?
Yes, yeah. Technically, you can treat as, factor out, yeah. All right, technically, yeah. All right. Okay, yeah. Then, after this understanding, the remaining, we compare the coefficients term by term. Yeah. All right, so the coefficients of, so this you can treat as x to the 0, that term. Okay, this is the coefficient to the x to the first, and so on. Okay, yeah. The remaining, because the remaining you can use general expression. For the first term, for the second term, you have to do special calculation, special cases you treat. Yeah, but general term you want to do more efficiently, so you can use the this way. All right, yeah. There, you get a recurrence relation. So this is the recurrence relation. Yeah. All right. Yeah. But when you get this recurrence relation, yeah, you need to, understand a sub s plus 2 equals something multiply a sub s. Yeah. To s. When you calculate a sub s plus 2, you need to use the value of a sub s. Yeah. The difference of the two subscripts is by 2. By 2. Yeah. So this property tells you all the even terms, all the coefficients of even terms are correlated, governed by this formula. All the coefficients for the odd terms governed by this reason. Two parts. Okay, even coefficients, odd coefficients. Yeah, two separate parts. Okay, all right. Yeah. So the first two. Yeah. So we can use. Oh yeah, so here, actually, the understanding of the solution structure. Yeah. The solution, y, we can write it as a sum of two components. Here, y1, y2, we treat as two components of the solution. Yeah. y1 component collecting even terms. Yeah. Even terms. And y2 components, yeah, because A1 is odd, right? Yeah. A0, the even, yeah. So y2 function collecting all the odd terms, yeah. Because even terms, you can use this recurrence relation. Odd terms, you can also use the recurrence relation, right? Yeah. So that's the, for some convenience. Okay, things like convenience. You do not have to use this way, right? You do not have to, but if you use this way, a little better, right? Yeah, because you have some relatively simple representation. Because y1 you can write it explicitly. y2 you can also write it out explicitly. Okay, all right, yeah. So y1 you can see all the even terms. Right? Yeah. So you factor out A0 coefficient. Yeah. Even terms. Yeah. Because look at that. So here, let's When you calculate, so when you calculate A2, it is by A0, right? Yeah. When you calculate A4, you need to use the value of A2 and so on, right? Yeah? Yeah. All right. So that's why you can factor out A0 everywhere because A2 is certain multiple of A0. Okay? Certain multiple of A0. Okay? Yeah. And so on. Yeah. So that's why you can factor out A0. Then the remaining terms, you can see the remaining terms, the coefficients are known, right? No unknowns. Everything is known. Yeah. So y1 function is known. Okay. Similarly, y2 function, after you factor out a1, the remaining, all the coefficients are known. Yeah. Okay? Then, so this solution is determined by two parameters. A0, A1, you can choose arbitrary two parameters, right? Yeah? You can choose any A0, any A1. Yeah.
So that's how we know when to stop, is that when we use the recurrence formula, we'll be getting like a repeated value A2.
Yeah.
So like if we can write A4 in terms of A2, we can stop there.
Yes.
Because we've used A2 again.
Yes, yes, yes. And when you write solution, you just write the first a few terms, yeah, to get an idea. Yeah. Because we have a general formula, we don't worry. So any term, we can produce it by the general formula. So we don't worry, okay? But usually we just write the first few terms, you know.
So it's
Yeah.
not often that those, like that series expansion can be written as an elementary.
No, no. Yeah, because, Matthew's question, he said, is it possible, this series representation can be right, for example, like a, elementary function 2 sine x plus 4, 5 cosine x, things like that. Yeah, it's rare you can write. It's possible. The chance is very small. Yeah, it's possible. Yeah, or sometimes plus e to the x, whatever, something. But 99.99% of the time, you cannot. You cannot do that. Only a tiny little chance you can do it. Yeah. So we have later you will see we have some examples. So you can write as these nice functions, but in general you cannot. In general, whatever it is, you just write it out. Okay. Yeah. Yeah. Good. Yeah. So that's to help you understand better. Yeah. All right. Now let's continue. Yeah. Oh, yeah, so here, remember convergence radius. Yeah. So this when x absolute value, because our center point is at 0, right? Center point is at 0, okay? Yeah, because this x, we treat it as x minus 0 to the 5th. This is in our Taylor theorem, that's the a equal to 0. A equal to 0, so our convergence radius, so this is A. Convergence radius, so here, okay? Yeah, this one, the convergence interval, radius is 1. Radius is 1, okay? Yeah. So this tells us in this interval, it is convergent. If it's not in this interval, it's not convergent. Okay? But you may ask question, how do you know this convergence radius? Yeah. Right? We have general term, right? You have general term here. Okay? General term. Then we plug in, we can calculate. Later, you will see that formula. We plug in into that formula, we can calculate. We find the radius is this number. Okay? Yeah. So later, when we get a formula, you can try, you can plug in and see. Yeah, what's that? All right. Yeah. Here. All right. Yeah. Yeah. S. All right. Yeah. Yeah. Later we will see that. Yeah. Because here we have these formulas. Yeah. Yeah. after we see the formula, we can plug in these coefficients to calculate. Yeah. All right, yeah. B.2, polynomial solutions and Legendre polynomial. Yeah. Here, why we talk about polynomial solutions? Yeah. You know polynomial. Everybody knows the polynomial, right? Can you view the polynomial as a special case of the power series? Right? Special case of the power series. Because for the polynomial, when m greater or equal to, let's say, some number k, all m equals 0. That's polynomial, right? That's the polynomial. Yeah. Yeah. If your power series has this property, when m greater or equal to some number k, fixed number k, then all the a coefficients become 0. Then your solution is a polynomial solution. Okay? Yeah. So it's possible. Yeah. Sometimes, you know, the Legendre polynomials. Yeah. So we can have this property, polynomial solutions. Yeah. All right. Yeah. So let's look at the polynomial solutions. Yeah. Reduction of power series to polynomials. Yeah. If you can have polynomial solutions, that is much better, because you have a complete representation, right? You do not need to use approximation, infinite many terms, yeah, because polynomial, you know, so that's a good function, yeah. So, all right. Yeah, another good thing about polynomials, without convergence restriction, yeah, because everywhere when you have a polynomial solution, you plug in any x, you have a valid value, right? Yeah, you never need to consider convergence issue, right? Yeah, no convergence issue. Only when you have infinite series, you have convergence issue, right? When you have finite many terms, you always get a valid number. You do not have that convergence problem. Okay? Yeah, so that's, you know, another important reason. So we like to, if it's possible, we like to have polynomial solutions. Yeah. Now, let us just look at the recurrence. We do not need to do anything. We just examine our old recurrence relation carefully. You can discover. So actually, it's a polynomial solution. It's not an infinite series solution. Yeah. All right. So let's examine. Yeah. That's the recurrence relation. That's recurrent. N is a fixed number, right? So n. Yeah. S keeps changing. Yeah. The subscripts for different terms, you know, S is different, but n always the same number, right? Yeah. Yeah. So now, if your S hit that n, sooner or later your S hit that n, happens to be that n, then that term is gone, 0. Okay. Then if a sub s plus 2 equals to 0, then the next term also 0, right? Yeah. If a sub m plus 2, because s equals n, equals 0, then you plus another m plus 4, also 0, because multiple of 0. Yeah. One number, you multiply a 0 number. Yeah. All the remaining coefficients of the even terms, 0, right? Yeah. Yeah. All right. So the y1 function is a polynomial function. Yeah. Polynomial when n is even. Okay. When n is even. All right. When n is even here, yeah. But yeah, when n is odd, y2 function is 0. Yeah. but not both. Yeah, here it's not both. Yeah, all right, all right. So derive the polynomial coefficient. Yeah, yeah, because here polynomial coefficient you do iterations. Yeah, so when, yeah, so here when n is even, when n is even, yeah, yeah. So you collect. Yeah, so you collect. Yeah, because the finite many multiplications you need to do. Yeah, yeah. Although, you know, you need to do very carefully. Yeah, so that's the result, right? Yeah, yeah. All right, so Legendre polynomial of degree n. Yeah, so there is a, yeah, so that's the degree n definition of Legendre polynomial. Okay, yeah. So the highest degree term, yeah, lower, you know, then you reach the, because in this way, yeah, yeah. So this general representation, yeah, so it's, you know, yeah. All right, yeah, just the, you know, special case, yeah, yeah, yeah. All right, yeah. B.3, extended power series method, extend. So yeah, we did extended thing quite a lot, several times. Yeah. The first time, extended separable ODEs. Yeah. The second time, that extended, you know, exact type ODEs. Yeah. All right, so here, extended power series method. The question, how do you extend? Right? Yeah. Power series, look at the power series. Yeah, that form. Yeah. Power series form. All right. Let me explain why we need to do this extended way. Okay? That question. Yeah. Why we need to do extended way. Yeah. All right, so let's recall. Yeah, because we did the extended things twice before. Let's recall our own experience. The first time, we extended separable ODEs. The question, why we look at the extended separable ODEs? Yeah, same logic. The reason is because we want to use that separable method to cover more ODEs, right? Extend it to cover more, okay? To cover more. Some ODEs originally, they are not separable, but after we do some suitable variable substitutions, we make them separable, okay? Yeah, so that can make us solve more ODEs by the separable method. Yeah, that's the first time. Second time, exact ODEs. So, you know, that form. We need to check the exactness condition. Yeah. But many times, exactness condition not satisfied. Yeah. There, we need to find appropriate integrating factor to extend it, to make it exact ODEs. Yeah, that's our second time, extended. All right. Now, here, the third time, extended power series method. Yeah. So the reason, straightforward, yeah, like this. Because power series representation is not enough to represent the solution form. Power series is not enough to represent the solution form. So we have to consider extended way to make it suitable to represent the solution form. That's the main reason. Yeah. Now let me help you understand. Yeah. So you may wonder why power series representation is not enough sometimes. Yeah. Very simple. Yeah. We still look at the Euler-Cauchy equation. Okay? Yeah. Euler-Cauchy equation. And our y we take. Yeah. But this place, although single term, very simple, but the m could be non-integer real number. Yeah. Now, yeah, so, and most of our solutions, non-integer solutions, think about if this m is non-integer, how can you represent it as a power series? Because integer, you only use the x to the integer terms to represent. It's hard to represent. You know, yeah, let's say the simple example, x to the 1/2. How to represent? Right? How to represent? Yeah. Very hard. Yeah. Very hard, right? As function simple as this one, if you want to use a power standards, this is standard power series to represent. Very hard. Yeah. Yeah. Why it's so hard? Okay. Yeah. Why it's so hard? Because structure-wise, they are not compatible. Okay. These two structures, they are not compatible. So they have quite different structures. How to make them look the same? Impossible, right? Impossible. Yeah. So for that, yeah, in order to cover the cases like this, you need to extend your power series representation to make the structure compatible. Okay? Compatible. Yeah. All right. So then, first give you a simple idea. How to make it compatible, right? Yeah. When we talk about extend, we change a little bit, right? Yeah. We still preserve the main part of the power series, but we change it slightly, right? We do not need to make a substantial change. All right? Yeah. So let's consider we do change like this. Yeah. X to the 1/2 times a power series. How about that? We consider this power series. Then it's compatible with this one, right? We factor out x to the 1/2. The remaining part could be a power series. If we use this structure, this is our extended power series structure. Yeah. It's different from the standard power series. It's extended power series structure. How about that? Then we can cover more cases, right? Yeah, we can represent more solutions. Yeah. But here, in general, so 1/2 just special case. In general, we use a variable x to the r. Yeah, the r could be any number, right? Yeah. X to the r times a power series. How about that? And we can determine that r. Okay, so which r is an appropriate r we should use for this extended power series representation? That idea. Okay? Then we can cover more ODE solutions. Yeah. Yeah. Think about this idea. Okay? Yeah? Small change, just the one extra x term at the beginning of the power series. You solve the problem. Okay? All right, so let's look at an example. Yeah. Yeah. Frobenius method. All right. How to extend the power series. Yeah, with that understanding. Now, yeah, let's look at the result. Okay. Yeah. Idea. Part times logarithm or times a fractional. Yeah. It could be a log function. Yeah. Sometimes you need to times logarithm. Then fractional power of x, that r. Okay? Yeah. All right. This is the Frobenius method. All right. Let's look at the content. Yeah. Let b of x and little c of x any function. Yeah. So this is the standard function we want to solve by this Frobenius method. Yes. Yeah. Yeah. And they're analytic at x to the 0. Yeah. Analytic. Yeah. Definition of analytic. Yeah. Infinite many derivatives. Okay? You can take infinite many derivatives. C infinity. Okay? C infinity. Analytic. Yeah. Yeah. Actually even stronger than that C infinity. Yeah. Yeah. All right. So you don't worry about, derivative. You can take infinite many derivatives. Yeah. Analytic. Okay? All right. Then the ODE, yeah, this form, standard form, yeah, ODE, yeah, has at least one solution that can be represented in the form. Yeah. This x to the r, okay? Yeah. All right. Yeah. Special case, yeah, where exponent r may be any real or complex, could be complex, okay? Even could be complex. Yeah. Number, and r is chosen so that a0 not equal, yeah, a0 not equal to 0. Yeah. Otherwise, you change your r. If a0 equal to 0, you consider, a1, you can take 1x out, right? Yeah, make it a1 the first coefficient, first the non-zero coefficient. Yeah. So you can choose to make a0 not non-zero. The ODE1 also has a second solution such that these two solutions are linearly independent. Yeah, because second order equation, two linearly independent solutions. Yeah, that may be similar to two, yeah, same form, yeah, but the coefficient different. Yeah, similar form. Yeah, yeah. With different r and different coefficient. Yeah. Yeah. The second one, yeah, you need to also determine r. Yeah. Yeah. Just like if you recall our Legendre equation, yeah, y1, y2, right? y1, y2. y1, y2, that r is different. Yeah. R could be integer. Yeah. After the factorization, if we want to do factorization. Yeah. Yeah. So r, if it's integer, it's okay. Yeah. Yeah. All right. Yeah. Yeah. Or may contain logarithm term. Yeah. Yeah. Logarithm case, we need to look at theorem 2. Yeah. Yeah. This Frobenius method. Okay. Yeah. All right. Yeah. Initial equation. Yeah. So here, remember we used the characteristic equation before, right? Characteristic equation. Yeah, we solve second order ODE. Yeah, the lambda, characteristic equation. Yeah. Yeah, but here, there is some equation similar to that characteristic, but we need to use that equation to determine R value. What's the R value? Yeah, we need some equation to determine. Yeah, so for that reason, we need to use a different name. Yeah, so that's the name. Yeah. This initial equation. Yeah. All right, two forms. Yeah, yeah, so this form, we remove the denominators. Yeah, the two forms. Yeah. All right, so we consider y solution in this form. Yeah. The R to be determined. Our first thing, we need to determine R. Yeah. After we determine that R, then we use that R. We plug in that R. But the R, because that initial equation, when you solve that equation, you may have more than one roots, right? The R1, R2. Yeah. R1 for the first solution, R2 for the second solution. Yeah. Two different R's. Yeah. All right. Yeah, so let's plug in. We want to see what equation this R should satisfy. Yeah.
This slide is missing on
let me see. Really? Oh, yeah, I didn't change anything. This slide.
If you want to look,
Oh, really? I remember.
I think,
Yeah.
check.
Oh, okay.
So we go from Chandra
Oh, yeah.
and that goes
Oh,
to this.
well, that's the B.4. Now I'm in B.3. I'm in B.3. Yeah. So you B.3.
Oh, you're.
Yeah, I'm here. B.3.
Oh, okay.
Yeah. All right. Yeah. So we go a little slow. Yeah. So yeah, today, yeah, if we can finish B.3, yeah. So that part, yeah, next time. Yeah. All right. Yeah. So slower than expected. The thing is because it's very complicated. Yeah. So that's why we would rather slow a little bit. Yeah. So many details we need to understand. Yeah. So that's why, in order to make sure the learning quality, yeah, let's going a little slower. Yeah. All right. Yeah. So we are at B.3. Yeah. All right. Yeah. So here, to determine that initial equation, yeah. So we calculate first derivative. Yeah. So here the technical details. So here I do not explain technical detail. Okay. So I assume you can understand. Yeah. All right. Yeah. Yeah. Because we, in our assumption, yeah, we assume A0, not yeah. So then second derivative like that. Yeah. Technical detail. Yeah. So if you cannot understand, you let me know. So I will, explain. Yeah. All right. So then the B function, we should also use the power series representation. Remember, we assume analytic, right? Remember in the theorem, analytic. So, we can do that. Yeah. Under that condition, we don't worry. Yeah. B function, C function, they have good power series representation. Okay? Yeah. So we just, use, yeah. But the B coefficients, C coefficients, because B function should be known, C function also known. So B coefficients, C coefficients should be known. Okay? Yeah. Should be known. Otherwise, too many unknowns. We cannot determine. Yeah. So B coefficients, C coefficients, all known. Yeah. We can use these coefficients to determine unknown coefficients. A coefficients unknown. Yeah. So we would calculate. Yeah. All right. So let's plug in. Yeah. The power series and yeah. All right. Yeah. So all these terms. Yeah. All right. So after factorization, yeah, because this x terms, you can cancel out, right? Yeah. So you can cancel out. Yeah. All right. But there is one thing. Yeah, this equation. Yeah. Equal to 0. Yeah, that equation equal to 0. Yeah. Right. So here, yeah, so you can see, yeah, so that's the initial equation, yeah. Because when you add them up, so you can see you need to make this equal to 0 so that you can find a solution. Yeah. So this condition must be true in order to have a solution. Yeah. Otherwise, structure-wise, it's not compatible. Okay? Yeah. Think about that. Yeah. So this is the, this initial equation you need to use to determine R. Yeah. Solve this quadratic equation with two roots, R1, R2. Yeah. Otherwise, think about this not equal. Yeah, because the remaining part equal to 0, then there is an extra part. It must be 0. Yeah. The extra part, if not 0, then yeah, because that term, yeah, this term contains x to the r. This term, it does not contain x to the r. So separate from that, both should be 0, right, to have a solution. Yeah. So that's why, this equation must be satisfied. Okay. Yeah. So that's this this equation. Then we consider cases, yeah, because the quadratic, you solve quadratic equation, you have the cases. Distinct roots, the first case, distinct roots not differing by integer. The difference is not an integer. Yeah, R1, R2. So if you, because you have R1, R2, two numbers, the difference is not an integer. That's case one. Case one, the simplest case. Okay, simplest case. Not integer. R1, R2. Yeah. Take difference, not integer. Yeah. Then you just plug in R1, we find a Y1 solution. Plug in R2, you find Y2 solution. Yeah. First case. Yeah. Case two, when the difference is integer, then you should do things differently. Yeah. You cannot, because you plug in R1, R2, basically you get the same solution, right? Because difference is integer, you factor out, you know. Difference is just, you know, yeah. So, case two, a double root. Yeah, double root, you do not consider it. Yeah, double root. Case three, roots differing by an integer. Yeah, so then your solution, you should take a different way. Yeah, so these three cases. Yeah. And the extended power series form should be different. Yeah. The first case simplest. Yeah. You just use R1, R2. Yeah. Get two solutions. Two linearly independent solutions. Yeah. But second to double root, then you need to multiply that logarithm, remember? Logarithm function, right? Yeah. Yeah. Things like that. Okay? All right. Yeah. So yeah. Let's look at case one. Yeah. Case one, you plug in R1, you find the first power series solution. Plug in R2, you find the second power series solution. Straightforward. Yeah. Yeah. So very easy. Yeah. All right? Yeah. Yeah. So that's the, you know, yeah, original. Case 2 and 3. Yes. Now, double root. So your Y1, so you still use that R, you know, the root number, but Y2, Y1 add natural log X, then plus that. Y1 times the natural log term. Okay? After that, then you determine another set of coefficients. That's the double root case. Okay? Yeah. Case 3, root differing by integer. Yeah. Yeah. All right. R1. Yeah. So R1, you still use the all the way R1. But Y2, yeah. Y1 natural log K. Yeah. Remember the difference in integer, right? Yeah. Root. Yeah. The K. Right. K is that difference of that integer number. Yeah. You take difference. R1 minus R. Yeah. So here, let's write this way. Yeah. This number, right? Yeah. Yeah. This number equals K. Yeah. All right. Yeah. So then R2. So you determine another set of coefficients. Yeah. So that's the, you know, this Frobenius method. Yeah. Case 1, 2, 3. Yeah. 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 But when you plug in, you need to do a lot of calculation. Yeah. So here, when I give you a question, I will pick relatively easy equations. So the calculation, I try to make it not too hard, too messy. Yeah, because sometimes when I do myself, still pretty hard. Yeah. So I try to make the question, you know, reasonably not too hard. Yeah, not too hard. Yeah. So you, the main idea is you just get some basic experience. Okay, some basic experience. You know how to solve it. Yeah. Okay. All right. Yeah. So that's the power series. So I think, yeah, although after the theoretical part, the remaining, we need to work on some examples. So then we complete this power series part. So that's all we need, okay? Power series part. So then in our homework assignment number 3, I need to give you homework assignment number 3 this week. Yeah, this week. Part A, Part B. Yeah, let me see, Part A, Part. Yeah.
When will you have our next quiz?
Yeah, next quiz, also this week. Yeah, so I want to post, the last weekend, yeah, but, I'm working on other midterms, so too busy, yeah. So I delayed a little bit. Yeah, Matthew? Yeah.
Can you say for the next homework assignment, part A will be our quiz 3 and the part B will be?
Yes, yeah. Right, I said.
Or like put them together?
Yeah, put it together. Yeah, yes, I said. Then the last one, yeah. Then the final, yeah. So the next one I split. Right now we complete 4 quizzes, right? Yeah, we have 2 more to go, right? Yeah. So we use 1 for next and 1 probably I use for final. Yeah. And homework assignment number 3 is probably yeah. So we just do it together. Yeah, homework number 3. We do 1 assignment together. Yeah. Related to Fourier analysis. Yeah. All right. Yeah. So let's do it in this way. Yeah. This weekend I will post quiz and computation questions. Yeah. Quiz 10 questions. Then computation. Yeah. The part B still 5 concept questions and 10 computation questions. Yeah. Otherwise 15. Sorry.
What assignment? You said we're doing homework 3 in class. Where are you going?
Not in homework 3 part A quiz. Part B 5 concept questions plus 10. I always give you 10 calculation questions.
Part A is our quiz.
Yeah, is your quiz. Part A is your quiz. Yeah.
And then one more, after that, one more quiz.
After that, 1 more quiz, but I want to use that quiz for your final because I want to save your time in class. Okay?
So no homework over the 4 years.
Yes, there is a homework number 4.
Okay.
Number 4, that's the Fourier.
This next one is 3.
Yeah, next is 3. Yeah.
2 homeworks.
Yeah.
Quiz.
Right. 2 homework, 2 quiz left. Yeah. All right. Yeah. Okay. Yeah. That's it.